There is a harbor in Italy that has been standing, largely intact, for more than 2,000 years. Built under the Roman Emperor Trajan around 110 CE, it's still there, submerged, partially eroded, but structurally sound. The concrete piers and breakwaters that Roman engineers poured into the Mediterranean are still holding together. Meanwhile, modern concrete structures, bridges, buildings, seawalls, built with what we consider advanced material science, begin deteriorating within decades. Some need major repairs within 50 years. Most won't last a century. This is not a romantic exaggeration. It's a materials engineering problem that has baffled scientists for decades. Roman maritime concrete, the specific mixture they used for underwater construction, gets stronger over time. Our concrete gets weaker. Theirs was made with volcanic ash, lime, and seawater. Ours is made with Portland cement, the most widely used building material on the planet. And yet, by almost every measure of durability in marine environments, we have not surpassed what the Romans achieved 2 millennia ago. In some ways, we've gone backwards. To understand why Roman concrete is superior, we first need to understand why modern concrete fails. Concrete is a composite material. You mix cement, a binding agent, with aggregates like sand and gravel, add water, and the resulting chemical reaction, called hydration, produces a hardened solid. Modern concrete uses Portland cement, invented in the 19th century. It's made by heating limestone and clay to extreme temperatures, then grinding the result into a fine powder. When you add water, it forms calcium silicate hydrate, which binds the aggregates together. It's strong, predictable, and cheap to produce at scale. But it has a critical weakness. It's vulnerable to chemical attack. In marine environments, seawater, saltwater spray, coastal exposure, modern concrete deteriorates through several processes. First, chloride ion penetration. Seawater contains chloride, which seeps into the concrete's porous structure. When it reaches the steel reinforcement bars inside, it causes corrosion. The steel expands as it rusts, cracking the concrete from within. Second, sulfate attack. Seawater also contains sulfates, which react with compounds in Portland cement to form expansive crystals. These crystals grow inside the concrete matrix, creating internal pressure that causes spalling, surface chunks breaking off. Third, alkali-silica reaction. If the aggregate contains certain types of silica, it can react with the alkaline pore solution in the cement, forming a gel that absorbs water and expands, cracking the concrete. And fourth, simple erosion. Waves, tides, freeze-thaw cycles, and mechanical abrasion gradually wear away the surface. The fundamental problem is that modern concrete is static. Once it hardens, it doesn't change except to degrade. Cracks don't heal. Chemical damage accumulates. The structure weakens over time. Roman concrete, by contrast, is dynamic. It continues reacting with seawater long after it's been poured. And those reactions don't weaken it. They make it stronger. So, what did the Romans do differently? Roman maritime concrete, the type used for harbor construction, was made from 3 primary ingredients. First, volcanic ash, specifically a type called pozzolana, found near the Bay of Naples. This ash was rich in silica and alumina. Second, lime. Produced by heating limestone, just like in modern cement production, but used in a different ratio and reacting with different materials. Third, seawater. Not freshwater, seawater. They would mix the pozzolana and lime together, then add seawater and chunks of volcanic rock as aggregate. The mixture would be placed into wooden forms submerged in the ocean, where it would harden over time. When the lime and volcanic ash mix with seawater, a specific chemical reaction occurs. The seawater, which contains dissolved sodium, magnesium, and calcium, reacts with the aluminous and siliceous materials in the volcanic ash. This produces a binding matrix that's fundamentally different from Portland cement. Instead of calcium silicate hydrate, the primary binding phase in Roman concrete is a mineral called aluminum tobermorite. This is a rare, extremely stable calcium silicate mineral that forms at high temperatures in nature, but the Romans managed to create it at ambient seawater temperatures through their specific mixture. Aluminum tobermorite is incredibly durable. It's resistant to chemical attack. It doesn't corrode. And critically, it grows over time. Here's where it gets remarkable. As seawater continues to permeate the concrete over decades and centuries, it doesn't degrade the structure. Instead, it triggers additional mineral growth. The volcanic ash particles continue reacting with the seawater, forming more aluminum tobermorite and another mineral called philipsite, both of which fill microcracks and reinforce the existing matrix. This is a self-healing process. Small cracks that would, in modern concrete, propagate and worsen, instead become sites for new mineral growth. The concrete essentially repairs itself. And because the reaction is slow and continuous, the structure doesn't just endure for decades. It endures for millennia. For most of modern history, we didn't know any of this. We knew Roman concrete was durable. The evidence was literally still standing, but we didn't understand why. The breakthrough came from a team of researchers led by Marie Jackson, a geologist and engineer at the University of Utah, working in collaboration with scientists at the Lawrence Berkeley National Laboratory. In the early 2010s, they began studying samples of Roman maritime concrete taken from ancient harbor structures in Italy, places like Portus Cosenus and the harbor at Pozzuoli. They used advanced imaging techniques, X-ray diffraction, scanning electron microscopy, and synchrotron radiation analysis, which allowed them to examine the concrete's mineral structure at a microscopic level. What they discovered was that the concrete's mineral composition didn't match what you'd expect from an ancient, inert structure. It was still chemically active. They found aluminum tobermorite crystals growing within the cement matrix, crystals that couldn't have formed during the initial mixing and hardening process. These had grown over centuries of exposure to seawater. They also found philipsite, another zeolite mineral, which forms when volcanic ash reacts with seawater over long timescales. And critically, they found that these minerals were concentrated in areas where the concrete had cracked. The cracks hadn't weakened the structure. They'd become reinforcement zones. This wasn't just archaeological curiosity. This was a fundamental materials science insight with immediate modern applications. If you could design a concrete that heals its own cracks, that gets stronger in seawater rather than weaker, you could build coastal infrastructure, seawalls, offshore platforms, tidal energy installations that wouldn't need constant maintenance and wouldn't fail after a few decades. You could reduce the environmental cost of concrete production, which currently accounts for about 8% of global carbon dioxide emissions, by creating materials that last longer and require less frequent replacement. This is not theoretical. This is engineering. So, here's the obvious question. If Roman concrete is superior for marine construction, why aren't we using it? The answer is more complicated than you'd think. First, volcanic ash. The specific type the Romans used, pozzolana from the Bay of Naples, has a particular chemical composition that makes the reaction work. Not all volcanic ash is the same. You'd need access to geologically similar material, which limits where you can produce it. Second, curing time. Roman concrete takes weeks to months to fully harden, and it reaches its peak strength over years or even decades. Modern construction projects operate on tight schedules. Portland cement hardens in days. Third, tensile strength. Roman concrete is extremely durable in compression. It can bear enormous loads pressing down on it. But it's weak in tension. It doesn't flex well. It cracks under bending stress. Modern structures often require tensile strength, which is why we use steel reinforcement. But steel corrodes in seawater, which is part of why modern marine concrete fails. The Romans didn't use steel rebar. They built massive, thick structures that relied entirely on compressive strength. But researchers aren't trying to exactly replicate Roman concrete. They're trying to adapt the principles. There are now experimental projects using engineered volcanic ash substitutes, fly ash from coal plants, ground blast furnace slag, synthetic pozzolans, to trigger similar self-healing reactions. Some teams are developing bioconcrete, which uses bacteria embedded in the concrete matrix to produce limestone when cracks form, sealing them from within. Others are working on polymer-based self-healing systems, where microcapsules of healing agent rupture when a crack forms, filling the gap. All of these approaches are inspired, directly or indirectly, by the realization that Roman concrete wasn't just durable by accident. It was durable by design, even if the Romans didn't fully understand the chemistry. The story of Roman concrete is not about lost ancient wisdom. It's about the consequences of optimizing for the wrong variables. We have the knowledge to build materials that last millennia. The chemistry is understood now. The mechanisms are mapped. Researchers have reverse-engineered the formula. What we lack is the will to prioritize durability over speed, longevity over cost, and the long-term health of infrastructure over short-term economic returns. The Romans built for permanence because they thought in terms of empire. Structures meant to last centuries, meant to project power across generations. We build for replacement cycles. And 2,000 years from now, when archaeologists are excavating what's left of our civilization, they won't find seawalls and bridges still standing. They'll find rubble,